Hello and welcome again to my Physics Online video lecture supplement series. In today's video, we're going to be looking at the 10th set of lectures for a Physics 2 course, which is the set discussing electromagnetic waves. And basically what this lecture set is going to be about is that we have previously throughout these lectures investigated mechanical waves, and we have investigated all sorts of electrical and magnetic phenomenon, but very rarely have we investigated all of these topics together, as it were. So we've investigated mechanical waves. Basically, in this case, you have a mechanical disturbance in some sort of media. They can be transverse or longitudinal, which basically means that the disturbed media is oscillated either parallel to or perpendicular to the direction in which the wave is propagating, and they require some sort of medium that can be disturbed. For example, you could have a wave in water, or a wave on a string, or a wave in air, but you don't get these mechanical waves in vacuum. Today we're going to be looking at a different kind of wave, which is electromagnetic waves, and these were first described successfully by Maxwell and then first observed by Hertz. So what we're going to look at today is Maxwell's description and then Hertz's discovery, and also how you can basically generate electromagnetic waves. How are they produced, in other words? And what this starts with is some modifications to some previously stated laws. The first one is that we have Gauss's law, and I have previously kind of danced around it as applied to fields other than electric fields. Basically, we'll look at it today as applied to magnetic fields. Second, there's what's called a displacement current that can be added to modify Ampere's law. And so in Ampere's law, it will no longer just be current or conduction current that causes a magnetic field, but in fact also a displacement current. And what Maxwell did was he first of all found this displacement current, but then second took these laws and sort of synthesized them along with Faraday's law, and collectively this produced what would be called the most important equations of all electromagnetism. He kind of created a theory that unified electricity and magnetism from two separate fields into one coherent field. And this unifying theory ultimately predicts electromagnetic waves, which then were observed by Hertz. So let's revisit Ampere's law and see what it is that happened. Basically, Ampere's law says that if you have some arbitrary closed path and you take the dot product of the magnetic field with some little section of length on this path, and then you add up those dot products going all the way around the complete closed path, then that sum will be equal to mu naught, the permeability of free space, times however much current is enclosed by the or passes through the area which is enclosed by or bounded by that path. So usually we think of our arbitrary closed path as being something like this kind of orange-red line, and then this tan thing is what would be the area bounded by it. But this law doesn't actually state that we have to use any particular path. It just has to be a closed path. We could have made it a more regular thing like a square or a circle or a triangle. And for that matter, we can make the area both flat, as in this picture, or we can have it be something that kind of bows out away from the closed path. So here there's two surfaces, surface 1 and surface 2, and Ampere's law should work for both of them. In this case, it obviously will, because this wire protrudes through both this bowed out area and this flatter area, so you have the same amount of current enclosed in both. The problem comes, however, when you have something like this. This is a pair of parallel plates. In other words, it's a capacitor. And if you look at the surface in this case, here's our surface 1, here's our surface 2. Surface 1 is, they're both enclosed by path P, this dashed line. Surface 1 is flat and the wire passes right through it. So any current in the wire is going to pass right through this surface. The problem is that surface 2 basically ends up being still totally bounded by this path, and as you look at this surface, it basically bows in such a way that it fits between the two plates of this capacitor, and therefore the wire does not actually protrude through surface 2 at any point. So that means that while we have a current that is passing through this blue surface 1, we have no current passing through the tannish, gray, whatever color you want to call this, tan brown surface 2. And so that means that for surface 1, mu naught I equals 0. For surface 2, mu naught I equals 0. So not 0, 0. But since both of these surfaces are bounded by the same dashed line, we would expect to get that this mu naught I and this mu naught I must be equal, because this same dashed line has the same, therefore, sum of magnetic field dotted with path length. So we basically have a contradiction. We're saying that that sum of the magnetic field times the path length must be at the same time both 0 and not 0. So this would rather violate the law of non-contradiction. So what Maxwell did was he found a solution to this, and that solution is basically called displacement current. And what he did was he said, okay, this current runs up to these two plates. There is no charge passing between the plates, and hence there's no conduction current, but there is conduction current within the two wires. So conduction current is basically the motion of charge carriers within a conductor. That happens here, that happens here, it does not happen here. But what does happen here is that as this current runs up to the plate, and as this current runs away from this plate, you're basically building up a plus charge here and a minus charge here. And what that means happens is that you're changing the electric field strength between the two plates. So if you have a pair of parallel plates and that's your capacitor, the charge must be the capacitance times the voltage drop between the two. And in turn, the charge itself, as it increases or decreases, is going to also change how much electric field you have here. And that's just by Gauss's law, or if you'd rather, you could think of it as you add some charges to these plates, you also increase the voltage drop between this plate and this plate. The electric field, for its part, is the voltage drop divided by this distance between the two plates. So as you increase the charge, you increase the voltage drop, which means you also increase the electric field strength. So you have a changing electric field strength in time. The current is basically equal to the permeability, the permittivity of free space times the plate area A, so that's the area of one plate, times the rate change of the electric field per unit time. Well, basically what Maxwell did is he says that this delta Q over delta T is the current, and that the electric field times the area of these plates, or for that matter times the area of any object, is going to be the flux of the E field through that area. And so what he did was he said that current is therefore, or this current here, is actually going to therefore be equal to the permeability of free space times the change in electric field flux per unit time. And so Ampere's law now gets generalized to say that B dot delta L, or the sum of the magnetic field dotted with the sort of length parameter of your arbitrary closed path as you go around the whole path, must be equal to permeability of free space times the conduction current that passes through the area bounded by that path, plus the permeability of free space times the permittivity of free space times the change in electric field flux per unit time, which is then called displacement current. So epsilon naught delta phi over delta t, delta phi e, change in flux for the electric field. This term is called displacement current. And so now Maxwell has basically fixed Ampere's law for the case of a capacitor, where there is no actual charge carrier passing from one plate to the next. So it's not just moving charges, but also changing electric fields that can cause a magnetic field. What's so important about that is that he basically took four laws: Gauss's law for electricity, Gauss's law for magnetism, Faraday's law, and this modified Ampere's law, and he summarized them into a set of predictions. The first prediction goes with Gauss's law for electricity. To a lesser extent, it goes with Coulomb's law. Basically says electric field lines must begin on a positive charge and end on a negative charge, and electric field is force per unit charge on a test charge. And then it's related to the permittivity of free space, which is this number here. Epsilon naught equals 8.8542 times 10 to the minus 12 farads per meter. And that comes out of Gauss's law for electricity. Second, magnetic field lines are continuous and closed, so they have no particular point of origin or termination. That means that there's no magnetic monopoles. These things form basically closed loops, and the magnetic field lines, the magnetic field strength must be related to the permeability of free space, which is 4 pi times 10 to the minus 7 Tesla meters per amp. And basically Gauss's law for magnetism says that if you take the flux through an arbitrary closed surface of the magnetic fields, you get zero, and so hence magnetic field lines are closed. Faraday's law is just that a changing magnetic field induces an EMF, and hence also an electric field. Really, it's that a changing flux of magnetic field induces this, because you can have a constant magnetic field and change the area or change the orientation of your loop. But this is Faraday's law. Then Ampere's law says that magnetic fields are produced by either moving charges, that is conduction current, or by changing electric fields, which is displacement current. And this changing electric fields thing is in fact actually once again a change in the flux of the electric field. So changing flux for electric field will produce a magnetic field. A changing flux for a magnetic field produces an electric field. One way that you can change the flux of either of these fields is just to change the field strength. When you combine those predictions with the Lorentz Force Law, you basically have the basis for all of classical electromagnetism. Basically, any classical electromagnetic interaction in a vacuum can be described by Maxwell's equations combined with the Lorentz Force Law. If you want to go inside of non-vacuum media, then you might have to modify Maxwell's equations a little bit, but you can in fact do it. Among other things, what these predictions put together actually predict, in addition to what's stated here, is they predict the existence of electromagnetic waves. And in fact, not only do they predict the existence, but they predict that an electromagnetic wave, once generated, can continue to propagate without there having to be any particular source media through which it must propagate. So electromagnetic waves can propagate through the vacuum. And Maxwell from there also predicted things like what speed do these electromagnetic waves propagate at, and he found that they propagate at the speed of light, and that therefore light must be some sort of electromagnetic wave, and it turns out that light falls within the electromagnetic spectrum. What happened next, though, is Hertz did his experiment, Heinrich Hertz. This is maybe a little after the time of Maxwell's death, sort of late 19th century. And what Hertz did is he basically made an RLC loop, which is this guy right here. That is a loop that has a resistor, an inductor, and a capacitor. And this thing ends up having a resonant frequency that looks like F naught equals 1 over 2 pi root LC. Note that this is just the same equation that we saw for AC circuits for an LC circuit, save that we've replaced the omega, which is the sort of the radial frequency, with F naught, which is just the frequency in terms of cycles per second. So basically he has this RLC loop, which he then has a second inductor, which forms a transformer, that makes another loop that ends with, as it turns out, just a capacitor. The capacitor basically is a spark gap. There's two balls here at the end of the wires. They're separated by some distance. As long as you don't break down the material between the two wires, charges sort of accumulate on these two ball ends and they stop. And so that basically means that you can build up until you reach an electric field of about 3 times 10 to the 6 volts per meter in air, because that is the breakdown field strength for air. Then he makes a second identical loop. Basically, it's actually identical to all of this minus the AC source. And so there's sort of an induced spark gap, or there's a spark gap across which is induced sparks, and then that's hooked up to a tuner, which basically looks like the back or the front end of this. There's a transformer and an RLC loop. And basically what happens is that he can tune the resonant frequency of this loop by sort of changing what the capacitance is, or changing the inductance, or changing the resistance, really by changing the capacitance or the inductance. And so he varied the capacitance until this whole thing was resonant with his initial loop. So loop 2 and loop 1 then have the same resonant frequency. And what he observed is that he could actually induce sparks across the gap when these two frequencies are matched. And he actually used a frequency of around 100 megahertz, which is comparable to the frequency used by an FM radio. So if you're driving in your car and you turn on the FM radio, you notice that you can sort of tune the dial and choose a channel between, somewhere in the 80s up through 106 or 107. And basically what those numbers represent is the resonant frequency that you're trying to receive. So if you tune your radio to 99.5 on the FM dial, it means that you've set a resonant frequency of 99.5 megahertz. So this is pretty comparable to that 100 megahertz that he actually used in his experiment. The choice of 100 megahertz largely is because of what was available as far as capacitors and inductors. Both capacitors and inductors tend to have what you might call a small value of capacitance or a small value of inductance. Milli or even micro tends to be a large capacitor or inductor. So basically what happened was that he picked his inductor, he picked his capacitor, he set them up in the loop. Omega goes like 1 over root LC. And so then he tunes the frequency of the receiver, matches it to the transmitter, observes sparks in the receiver spark gap. And what's so interesting about that is that he doesn't have anything over here in this spark gap to actually be powering these sparks. So what he basically called it a wave because this is analogous to a mechanical wave phenomenon in which you take a tuning fork and you strike it and then you hold it nearby a second tuning fork that is at the same frequency, say 512 hertz. And what happens is that in that second fork, it starts to induce some vibrations. And so his conclusion here was that this phenomenon is kind of similar to that other phenomenon, so they must be caused by similar phenomenon. Therefore, whereas the tuning forks, you get induced vibrations thanks to a mechanical wave, in this case you have an electrical circuit, so you're getting induced sparks and thus an induced current thanks to electromagnetic waves. So there are a few properties of electromagnetic waves which we won't necessarily investigate in depth today, but that are kind of interest to list. This, by the way, is a sort of nice artist rendition of what an electromagnetic wave looks like. You have your electric field, makes a sine wave. You have your magnetic field, it also makes a sine wave. The electric field and the magnetic field are perpendicular to each other, and both are perpendicular to the direction in which the wave is propagating. The wavelength is basically from peak to peak for either the electric or the magnetic field. In fact, they have the same wavelength. There were a few interesting properties that get observed. Among other things, Hertz observed many of these. For one, the electromagnetic waves can be reflected and they can be refracted. So reflection basically means the wave is going in one direction, it hits some object, and it sort of bounces off the object and now has changed direction. Usually if we say that this direction is along the z-axis, then some component of the direction has been reversed. May not be the entire direction, but it may be, maybe the object is at some angle to this. Then the portion of this which is perpendicular to that angle is sort of reversed, and the portion which is parallel is sort of continues. Refraction basically means that if you switch from one medium to another, then this wave will bend at that interface. That these are both observed in mechanical media, in mechanical waves, I mean. These will undergo diffraction, which basically means they kind of bend around sharp edges. Again, that's also true for mechanical waves. If you put a little slit in water and send waves at it, you'll notice that they kind of ripple outward from the slit. Another thing is that electromagnetic waves can interfere with each other and they obey the superposition principle. That actually is a principle that we talked about in depth in discussing waves. And last but not least, these have another property which they share with light, which is that they have polarization. The polarization of the wave is basically the plane in which the electric field is pointing. So if this is the XY plane, then the electric field is polarized in such a way that maybe it points along the x-axis only, or it could point along the y-axis only, or along the z-axis only, or some skew angle. So the polarization of the wave basically gives what direction does this light or other electromagnetic wave have the electric field oscillating along. So from this and from some of the other things that this shares in common with light, from the fact that they knew that light can also do all these things, they were able to basically conclude that light must be some sort of electromagnetic wave. Another interesting property that goes with electromagnetic waves, you see that both the electric field and the magnetic field are going to vary sinusoidally. So these are both equations that go with a plane sine wave, kx minus omega t, where kx is the wave number 2 pi over wavelength, and omega is 2 pi over period. So wavelength represents the spatial separation between two peaks. Period represents the time separation between two peaks. So here's one peak, here's the next peak. Here's one peak, here's the next peak. Finally, the speed is given by omega over k, or lambda times f, and it can actually be shown that the speed c is also equal to the maximum amplitude of both the E field divided by the maximum amplitude of the B field, or because these are in phase, in other words, k, x, omega, and t are all the same for both of these two equations, that the ratio everywhere of the electric field divided by the magnetic field is equal to the speed at which this electromagnetic wave propagates at. And that speed in turn is equal to 1 divided by the square root of the product of the permeability of free space and the permittivity of free space. In fact, if you go into non-vacuum media, this is true for vacuum. For non-vacuum media, it's basically equal to this times, or I should say divided by what's called the refractive index of the media, which basically ends up being how is that media modified as far as permittivity and permeability. So let's look at a few short examples of this before moving on to production of electromagnetic waves. So our first question is, if the maximum electric field strength of a certain electromagnetic wave is so much, 555,000 volts per meter, what is the maximum field strength of this wave? Well, magnetic field strength of this wave. Well, we have that E max over B max is equal to C, which is equal to 1 over square root of mu naught epsilon naught. So what we need to do here is basically calculate what the value of C is using this equation, and then also solve for B max. We can solve by rearranging. Basically B max is going to be E max over C. So what is C going to be equal to? Well, since C is equal to 1 over square root of mu naught epsilon naught, we can also write that C is 1 divided by square root of 4 pi times 10 to the minus 7 Tesla meters per amp times epsilon naught, which is 8.8542 times 10 to the minus 12 farads per meter. Plug these into our calculator. What we get is 4 times pi times 10 to the minus 7. So 10 to the minus 7 is like this. Multiply that by 8.8542. Multiply that by 10 to the minus 12. And this is what you get. So now we take a square root of it. You get 3.3356, etc. times 10 to the minus 9. But remember that this is 1 over c, so we basically invert it and you get 2.9979, etc. Usually I don't keep all the digits after that, but for what it's worth, the actual accepted value would be 2.9979248. So you can see that I rounded just a little bit with the epsilon naught. So if you want basically a more or less exact value, C is equal to 2.9979248 times 10 to the 8 meters per second. Oftentimes this gets rounded to 3.00 or maybe 2.998 times 10 to the 8. Okay, so that is your speed of light in a vacuum. Now, the actual question, though, asked what is the maximum value for the magnetic field. So, in fact, we do actually want to put that back on the bottom, and we want to multiply it by this value for the electric field, 555000. Whoops, 1 0 too many. And we end up getting 0.00185, etc. Teslas. So B max is going to be 0.00185 Teslas. I should note before moving on from this problem, you'll notice that every time you go to calculate the electric field strength or magnetic field strength from each other using magnetic field, or using this equation, E max over B max is C, or E over B is equal to C, that you're always going to get what looks like a much, much larger electric field than magnetic field. Again, that's because C is itself a very large number, about 3 times 10 to the 8. But it would be a mistake to therefore conclude that the electric field itself is always somehow bigger than the magnetic field. And the reason why is because these two fields represent two entirely different phenomena. They interact in slightly different ways with matter, and they certainly have different units. So an electric field interacts with charges, whether they are stationary or moving, and all that matters is how much charge is present. A magnetic field interacts with charges which are moving. And what matters there is not only how much charge is present, but also how fast the charge is moving. If the charge is moving at speeds that approach the speed of light, then you might find that the force that the magnetic field is exerting starts to approach the value of the force that the electric field is exerting on that same charge. So with that said, let's look at the next example. The next example says that if the frequency is 140 terahertz, and we're using frequency f, what is the wavelength? Well, remember that from mechanical waves, the speed was always given by lambda times f. This is also true when we do electromagnetic waves. You use c equals lambda times f. And so lambda must be equal to c over f. And so that is 2.9979, etc. We'll call it 2.998 times 10 to the 8 meters per second divided by 140 terahertz, which is 1.40 times 10 to the 14 inverse seconds, or hertz. So the wavelength that we're going to get basically should be, we'll do 2.998 8 divided by 1.40, you get 2.14 times 10 to the minus 6. So 2.14 times 10 to the minus 6 meters. So this is 2.14 microns is the wavelength. It turns out that that actually puts it kind of in the sort of near to mid IR range for what it's worth. We won't be talking much about spectrum of light in this lecture part, but in a future lecture set we may. So let's look at the third example. The third one says, if the above wave has its maximum electric field strength at 0 seconds, what will be the electric and magnetic field strengths after 5 picoseconds? Well, recall that basically you can use E max is, E is equal to E max times sine of kx minus omega t, and you can always add some phase term. And we can make this phase term such that this, at a particular location, looks like E max times cosine of omega t. And basically that's what this example is getting at, is at some position there may be a maximum field at time t equals 0, and this equation right here would satisfy that. So now we want to know after 50 picoseconds what is the E field. So E basically will look like E max times cosine of omega, which is actually 2 pi times f, times t, which is 50 picoseconds. So this becomes E equals 555,000 volts per meter times the cosine of 2 pi times 140 times 10 to the 12 hertz times 50 by 10 to the minus 12 seconds. So that's what that basically is looking like. And we can cross out some 10 to the minus 12s here. We could cross out some units, seconds, and you're left with 2 pi times 140 times 50. Now, I don't really need to multiply these out to be able to see what the result of this is, because 140 times 50 is going to give an even integer. So that means that we have the cosine of 2 pi times some integer value. And the fact that you have an integer times 2 pi means that cosine is going to be equal to 1. So all of this has a value of 1. So E, therefore, must be 555,000 volts per meter, and B will similarly be equal to that maximum magnetic field that we found earlier, the 0.018 Tesla, or whatever it was that we found earlier. I guess there were actually maybe 2 zeros in that, so 0.00185 or whatever Teslas. So those are our 3 examples. Let's move on and look at electromagnetic wave production. The basic way that you produce electromagnetic waves is that you accelerate charges. So any charge that's accelerating will produce, or alternatively will absorb, an electromagnetic wave. And basically, the way this works is that energy is either removed from or added to the charge via electromagnetic radiation. So, electromagnetic waves can be produced by causing charges to accelerate, mostly by causing charges to speed up or slow down, although a charge which absorbs a wave packet, which is called a photon, will also accelerate and can, in fact, turn, as well as speeding up and slowing down. So one method for doing this in a controlled manner is to use what's called an antenna. And the simplest version of an antenna is actually pictured right here. It's called a half-wave antenna. And it's sometimes also called a dipole antenna because the electric field lines, which are drawn here as these actually circular lines, more or less resemble the E field lines that you'd get from a dipole. It's more like an extended dipole. And in fact, if you look here, you have a bunch of positive charge, you have a bunch of negative charge, equal magnitude, and they're separated by some distance. It's not exactly a dipole. It would be exactly a dipole if all of these positive charges were located in one small cluster here, point cluster in fact, and all the negatives were at a point here. So it's not exactly a dipole because they're extended. So let's look at how the half-wave antenna actually works. In the simplest case, you could think of it as having a couple of rods which are conducting and that can be connected or disconnected from a battery via a switch. And if you close the switch, what happens is that you have a voltage which this EMF basically produces a sort of momentary current in which all of the positive charges flow up here to the top and all the negative charges flow down here to the bottom. And that basically creates this set of electric field lines thanks to there being charges. Furthermore, while these charges are moving, you get a magnetic field. And again, you can use your right hand rule to figure out the magnetic field. Point your thumb in the direction of the current, which is up, some thumb towards the top of the page, wrap your fingers around, and what you see is that on this side the magnetic field line is sticking out of the screen at you. On this side the magnetic field lines go into the screen away from you. Now these fields do not appear instantly everywhere in space. If this were a truly static case, for example, all the plus charges are up here, all the minus charges are down here, or even they're all distributed evenly along these rods, which might happen if you open the switch. If that has happened and it's been sitting there for a very long time, then yeah, there will be some extended E field lines everywhere in space nearby. But the E field lines and the B field lines take time to actually propagate when something changes. And when this switch is thrown closed, something is definitely changing. So it takes some time for example, maybe a detector over here. It would take time for this to register that there is now an electric field or a magnetic field present. And basically what this means is that even if you stop generating the electric field and magnetic field lines here, you can still get some propagation of the electric field lines out here in space. Maybe over at this point it registers the electric field line even after all the charges have somehow recombined. Maybe you make like a circuit of it to discharge the plus and minuses here. Well, it takes some amount of time for this point to even detect that there was charge separation and therefore that there is a field. And then sometime later that field disappears because there's no longer a charge separation. Also notice that using the right hand rule and using the drawing for an electric field that goes with this charge configuration, that you do in fact get that the electric field and magnetic field are perpendicular to each other. Okay, so this is the case when you're trying to just use a simple battery or other DC EMF source to drive this antenna. You sort of open the switch, charges can distribute, then you close the switch, charges maybe move towards the edges, and you can get a little bit of variation in the electric and magnetic field lines when that happens, and then once you reach a steady state, no additional magnetic field lines will be introduced, and only an electric field line will be sitting there, and it will be static and therefore not really changing once it's registered. You can, however, hook up a DC source rather than an AC source. You can hook up an AC source rather than a DC source. And what that does is that within the dipole, or within the antenna, the electric field direction changes, because initially you have all of the charge move down here, all the negative charge move up here. You get an electric field that goes from here to here. Then sometime later, up here is all the positive charges and down here is all the negative charges. So you get a downward pointing electric field line. And basically, as these things oscillate back and forth, as these charges oscillate back and forth, the strength of the electric field is going to be changing. And these oscillate in an AC system like a sine wave. And so therefore the electric field strength will also change like a sine wave. Furthermore, you can also look at what the current itself is doing. What the current itself is doing is it is moving back and forth like a sine wave. And this current generates a magnetic field. And so however much current you have, that's how strong the magnetic field is. That's just Faraday's law. That's just Ampere's law. Basically, that means that you're going to produce a sinusoidal magnetic field line. But the magnetic field line is going to be determined by the right-hand rule. Therefore, whereas the electric field line is vertical, the magnetic field line more or less is coming out of the page and going into the page, or coming out of the screen and going into the screen in this orientation. Of course, your magnetic field is actually making a closed loop at any given time. But what happens is that the electric field lines reverse direction in time, the magnetic field lines reverse direction in time, and so they both end up forming closed loops that then can propagate. And so these closed loops are propagating E field lines and propagating B field lines, which have no particular point charges that are moving along with them. So in fact, even if you shut off this antenna, this wave can continue to propagate because you have these closed loops of electric field lines. So that also means that this field is self-sustaining, not only if the antenna ceases to operate, but also if you enter vacuum or whatever. And what's important here about this is that it is in fact something that is predicted by Maxwell's equations, and only by having that modification to Ampere's law in Maxwell's equations, namely the displacement current, because you have now a changing electric field strength, which, thanks to the Maxwell's modification to Ampere's law, will produce a magnetic field. And since this is changing, the electric field is changing, the magnetic field will itself be changing. And a changing magnetic field by Faraday's law will produce an electric field. And so the electric and magnetic field lines are able to propagate together by sort of self-producing each other. The electric field produces the magnetic field, which in turn helps to produce more electric field. And so you get this wave able to propagate away from the actual charges that are moving within this source. So that's all that I wanted to talk about today. And this is part 1 of lecture set 10. Part 2 would look at stuff like the electromagnetic spectrum, and we'll also look at a few other properties of electromagnetic waves, such as how much energy do they carry and how much momentum do they carry and what kind of radiation pressure do you get, etc. So that's all for today, and hope you enjoyed this video, and thanks for watching.